So what we often do in physics problems is connect the rotational parameters to, and then the word to use here is very difficult to come up with. You could say translational, but that's not really right. Nothing's translating. What you mean is we want to connect that to how something is moving actually on the edge, right? So if I put this like red piece of tape on here where you can see it, now it's going around, right? And it's signifying one point of the edge of the disk. And if you think, if I look at it right here, I could imagine how fast it's going, right? It has a velocity. It doesn't just have an omega. If I count around how fast it goes around, that's omega. But if I get really tight on it like that, right, it has a velocity. So we have to connect the rotational parameters to what? To the translation of what? It has no name. I read a bunch of books. It has no name. I call it edge translational. I just made that up last night. I think it's going to catch fire. It's going to be all over Twitter. Edge translational. And what it just means is the translational motion of something on the edge. And if for a minute you imagine it's going straight on the edge, then it's our old things, velocity, etc. Okay? The other weird thing about this is when people want to talk about edge translational, as you'll be seeing by noon, it's going to be all over. Okay? It's classic. They're too excited. They have to get to omega. They're so excited about omega, they immediately define omega. And they skip the most fundamental thing in all of geometry, right? Which is the arc length. It's like if you did kinematics and you skip position, you just went straight to velocity. Well, we got to do the arc length, right? We got to do, this is basically the distance along really a curve, but we'll say the curve of a circle. We're kind of focusing on circular motion, even though we haven't formally said that yet, of a circle. Right? There's a formula to get that, right? So if we draw a circle like that, and it has some radius r, okay, and let's see, circle, radius r, and I go from here to here through some angle theta, then the arc length is literally this curved distance here along the edge. It's the curved distance. It's not this straight distance, draw a triangle in there. It's actually the distance along the curve. The formula, very simple, S equals theta r. Yes, this is really just how we get the circumference. But circumference is kind of like a formula you memorized. There is a general version of this. The arc length around a circle is theta times r. Let's look at how the units work out. What is the arc length in? It's in meters. Right? It's a length in meters. And what is r in? The radius is in meters. So what could theta be in then? So theta is in radians. So it looks like your units aren't working. That's kind of weird. That's because radians aren't really like a physical unit. Okay, we use them for angle, but if you see radian on one side and not on the other side, it's okay, because it has no like physical meaning. Really, you could say this is in median raters. No, it's in MR, whatever the hell. You know what I mean? Anytime you have a curve length, you could say it's in meter radians. Okay, but you don't really need to because the radians don't really exist. You can just say it's meters and meters. Don't worry about the radians. Okay. So that's one little intro to radians. Now let's, just to show it to you a little bit better, let's say the S, by S I mean arc length, is a fraction of the circumference. Clearly, the circumference, is all the way around, so S is a fraction of that. So let's just calculate that. S is a fraction of the circumference is over 2 pi r. The other thing that's a fraction of the circumference is the angle. Right? So if we have the angle theta in degrees over 360 degrees is all the way around. Right? So now let's turn this into the definition of arc length. So let's go to the definition of arc length and see what magical thing happens here. So let's see, this S, I'm going to take that over there and I want something times r. So what I'm going to end up with is theta in degrees times that pi went over there. The 2 cancels the 360 down to 180 times r. Okay. So when you're given a problem in degrees, this tells you kind of how to convert it to radians. You take the thing in degrees and you multiply it by pi over 180. Right? That's the conversion from degrees to radians. Because we know this number has to be that angle in radians. That's how this works. You can't have degree meters. You can only have radian meters. So if you have it in degrees, pi over 180, right? And that's why we have all these famous positions. This is 0 degrees and 0 radians, right? Therefore, 180 must be 1. So all the way around to here is 180 degrees, and it's pi radians. And this is 90 and pi over 2, and this is 270 and 3 pi over 2, etc. And then 2 pi all the way around. Okay? So I'm just trying to give you some feel that radians are like real. They aren't just some made-up factor multiplying degrees. I mean, it comes from the definition of a circle in geometry and things like that. But don't panic if it looks like your units aren't balancing. See, this is why I hate dimensional analysis. It's one reason. Okay? Okay. So let's see, what we were doing is we had our 3 rotational parameters, and now we're coming up with our edge translational parameters. That's what we were doing, believe it or not. So the first one was S. I didn't write it here. S, yeah. And now we're going to do 2 more. Good Lord. Oh, it's stuck. It's stuck. Should I fix it in real time? This has never happened before. There's a first time for everything. Oh, it's really stuck. Boom. Yes. Okay. 30,000 a year, folks. Here we go. Let's see. Okay, so another edge translational thing we want to talk about is how fast is the tape going. Right? If I just zoom in right here, it flies by at some speed. So that's, of course, what we call the tangential velocity. Tangential velocity. And basically, it's the velocity along the trajectory. And it is like your normal translational velocity. It's in meters per second. We use v to describe it. If something is going around here and it's going in a circle, you draw it like that. V, and we'll put a t on it to tell you it's the tangential velocity, like that. All right, so this thing's here, and it's at radius r, going around a circle. So what is it? Well, if we want to calculate it, its magnitude would be ds dt. Right? How much arc length is that thing passing by per second? So let's do some calculus, ds dt. So we want to take the derivative of ds dt. Well, we look at s. And we say, d what here, dt? Well, r is constant. That's just d theta dt. So it's d theta dt times r. D theta dt times r. Well, what is d theta dt? It's omega. Right? So the tangential velocity, if you want to write it in terms of the rotational parameters, you just take the rotational velocity and multiply it by the radius. That's pretty simple, right? That's how you get it. You're going to find that I promise you, remember I said the first 3 weeks is a lot of crazy, difficult vector math stuff, and then it'll chill out, right? So there you go. We have nothing that even has terms added yet, okay? The concepts now get more difficult, but the math gets a little easier. Now, often when we talk about this, it's often called the speed. So let's think, why would it be referred to as the speed all the time? And the answer is the direction is constantly changing. You wouldn't want to try to write this in vector notation because, well, right now it's pointing this way, but later it's pointing this way. It doesn't have a constant direction. The only thing constant is the magnitude, usually, if this is uniform motion. So if the magnitude is the only thing you can really characterize easily, the magnitude of velocity is often called speed. Okay, so in a problem, they'll often tell you it's going by and its speed is something. That's because they don't want to deal with the direction. They just want to give you the magnitude. Right? Okay, so VT is speed. Let's look at another one. 3 is the centripetal acceleration. That's fun to say if you've never said it before. Centripetal acceleration. How many of you have never raised your hand? No one. One. Okay, cool. Okay. Try saying centripetal acceleration as well. So centripetal means center seeking. Okay. So it's just the fact that this thing is accelerating. Now, which way is it accelerating? Is it what? It's in the center? Let's decide. So what is acceleration? A is delta v over delta t. If we give up the derivatives for a minute, we want to go back to finite intervals because we're going to try to draw this. Okay, so here we are. It started out here, and it was going kind of that way, right? Because this velocity is always tangential to the surface. Okay? So that was at 1, and this was at t1, we'll say. I mean, it's a radius, but it's at time 1. And then later, it's going like, let's say here. This is where you capture it at t2, and it's also tangential. So that's v2. So there's your two tangential velocities at two different times. So what is delta v over delta t? Well, don't forget, that's v final minus v initial. I'm going to call it, I screwed it, v2 minus v1. I should have called it initial and final. But that's the difference, v2 minus v1 over delta t. So if we want the direction, we just have to do the vector addition of v2 minus v1. And how do you do that? You draw v2, which is pretty much down like that. And then you draw v1 head to tail, but you reverse the direction. So it's kind of like, why is that going to suck? Let's see. Oh, that's why. Yeah, it's kind of like that, right? So there's v2 and there's minus v1. So what's the sum of those is like that. That's v2 minus v1. You divide it by delta t, well, and you've got the acceleration vector. So it's the same direction as the acceleration vector. And sure enough, just from our little drawing here, you see it points in, right? Center seeking. So you can get the direction just from a quick little drawing of v1 and v2 between two different times, if you put them far enough or close enough together. What about the magnitude? The magnitude is not as clear. We call it AC, the centripetal acceleration, and it's vt squared over r. Okay? I have a way I can derive it for you. It takes 10 minutes, and it's incredibly unsatisfying. Okay? So we're not going to do it. I have a video of doing it, the least watched video on YouTube. And I'll post it. Maybe it'll get up to 3 views. Okay? But yeah, it's just you can get there with some little geometry BS, but it's really not, it's not very insightful. So let's not bother. Okay? Just trust me, the centripetal acceleration is v squared over r. So we have omega r here, v squared over r there. Okay? These are sort of a few standard definitions. We're going to give you more definitions soon, because some of these are not what you would use in a problem. Like if a problem said calculate this, the tangential velocity, it probably wouldn't originally give you omega. It'll tell you like how long it takes to go around or something. So we'll show you how to do it with that in a little bit. I didn't write my name.